Oh no, I'm almost losing you. Okay, you're back. All right, what if instead of pulling on an object with a string, a wire, a cable, something that is an ideal string, cable, rope, and therefore doesn't stretch? What if instead I pull on it with something that does stretch? Something like a spring. So if I had a scenario where I have this spring and it's attached to a block, and I pull the block, or I push the block in. I either compress or stretch this spring from its equilibrium length. So all springs have this equilibrium length. This is the length that they're happy at. At that length, they don't count as being stretched or compressed. And they're perfectly fine. They're in what we call equilibrium, which means they are not creating a force. The force from a spring comes when you compress it or when you stretch it. There are lots of roller coasters in the world that use one of two things to get up their first hill. Either they use energy, which we're going to talk about later. So they add energy into the system by creating potential energy and then turning it into kinetic. That's the next unit. It's very exciting. Or they use a spring. They compress a spring. If you've ever ridden the rock and roller coaster at Disney World, this is a great example. Mr. Freeze at Six Flags also does this. You get into the ride, and it maybe moves you onto the track, and then the first thing that it does is it backs up. And you can honestly, most of the time, hear it compressing that spring. When the spring becomes compressed, it's going to then have a force. And when we let go of the roller coaster, that force is going to push it. Oftentimes, these are the roller coasters that get to 70 miles an hour right out the gate because that spring pushes it with all of this force giantly out to the side. Now, how much force did the spring apply to the roller coaster? Well, Hooke's law says that the force of a spring is equal to K times the distance that spring was compressed or stretched. So K is a spring constant. Every spring has a different one. It's the ability of the spring to compress or stretch. So the thicker, sturdier springs that don't really want to compress or stretch, those guys are going to have very, very large K constants. The ones used on roller coasters are going to have 3,000, 5,000, 100,000 K constants. That way they can build up a lot of force as they're compressed or stretched. The ones we're going to use in class we're talking 50 to 100 Newton per meter for spring constant. Spring constant unit is newtons per meter. That makes sense because if I multiply the spring constant, newtons per meter, times the distance, really the displacement, compressed or stretched, which is obviously in meters, well, Newton meters times meters is going to make newtons. So this is Hooke's law, but there's a little trick to it. So the amount of force is dependent on how much I stretch or compress the spring. But which way does it point? Well, if I compress this spring, so I have compressed it, and now my block is sitting right here. Which way does the block want to go? I've pushed the block to the left. I've compressed the spring. Its delta x right now from its equilibrium length would be a negative delta x because I've compressed it. It's negative delta x. I've compressed it a distance negative, right? Its displacement from its original starting point is in the negative direction. But which way is the force going to want to push? Is it going to push to the left or to the right? Well, if I compress a spring, it's going to want to uncompress and get back to that equilibrium length, so it's going to push me that way. So the force is going to point that way. This poses a problem for Hooke's law. The force is against the displacement. The force is pointing in the opposite direction of the displacement. Well, maybe that's a unique scenario. Maybe it only happens when I compress it. What about if I stretch it? I'm sure it's not the same if I stretch it. Okay, let's try. So let's say I have my equilibrium length here. And I stretch this guy all the way out to the block here. I've supremely stretched my spring. So its delta X is this really big amount here. Well, I've stretched it. I've pulled the spring out. Pull. Which way is it going to want to go? Which way is this force going to apply and make this block go? I've stretched the spring. Stretch. Which way is it going to want to go? Back that way, right? If I stretch a spring, it's going to want to go back to the equilibrium length. Always go back to the equilibrium length. So now it's going to have a force that wants to go. Did I write the force backwards? No, I didn't. It just looks weird. The force is going to want to go back that way. So now I have a negative force against a positive displacement. Oh no! So in both scenarios, the force is in the opposite direction of the stretch or compression. Whichever way I compress or stretch the spring, the force it's going to apply is going to be in the opposite direction. So Hooke's law is not complete. Hooke's law actually has a negative sign right up there at the front to help with this issue. So Hooke's law is that the force of a spring is equal to negative the K constant times the distance it was stretched or compressed. This is important because that means the force of the spring is not always constant. It depends on how much it's been stretched or compressed. So let's see an example with this. I'll use black, sorry. A block is attached to a spring horizontally and resting on a frictionless surface. We'll take friction out for today. If you pull the spring with a force of 20 newtons and it stretches 0.1 meters, what is the spring constant of the spring? What is the spring constant of the spring? So just like we do for every single force question, we are going to draw a free body diagram. So I'm going to assume that I'm pulling on this F pull to the right, and this force of spring is to the left. So I've got FG and FN. Fn and Fg. So if I write out an F net equation in the x direction, because that's the one I care about, that's the one that has force spring, I get F pull minus Fs. Now I've pulled the string and it's stretched I'm holding on to the object, so the object is not moving. So the net force is equal to 0. So F pull must equal Fs. So 20 is equal to negative K times delta X. 20 is equal to negative K. If this is positive, then that means I must have stretched it a length in the negative direction. That makes sense. I've stretched it. That's going to be a positive. So then K is equal to 200 newtons per meter. K is always constant. No matter what you do, K is always constant. So to wrap up, what we've learned today is that spring force is not constant. It depends on how much I have stretched or compressed the spring. That is shown by Hooke's law. Hooke's law tells me how much the force of the spring is going to be. We also have this negative sign in Hooke's law because if I compress the spring, it's going to want to stretch back out. And if I stretch the spring, it's going to want to compress back to equilibrium length. The spring always wants to go back to equilibrium length. So whichever way it's displaced is the opposite direction of the way the force is going to want to go. So in this case, this spring was displaced to the right, so it's going to have a negative force to the left. All right? That's all. See you in class.